This is the solution to quiz number 3 for ECE321 Analog Electronics. This quiz covers filter design, specifically Butterworth and Chebyshev filters and analog computers. The first problem, I want to design a filter that has a gain of at least 0.9 for the frequencies below 100 Hz, no more than 0.1 for frequencies above 400 Hz. To do that, you first find the order of the filter. If I have a single pole, the gain drops off as whatever frequency. As the frequency goes up by 4 times, if I have n poles, there's the gain roughly. The gain should drop by down to 0.1 as they go up 4 times in frequency. That says they need at least 1.66 poles. So let's round up to say 2 poles. Actually, I can build a third order filter just as easily as the second order. So let's call it 3 poles. Once you pick the number of poles, pick your favorite type of filter. I like Chebyshev filters, so let's pick a Chebyshev filter. If I have a third order Butterworth or third order Chebyshev filter with a corner at 1, here's the transfer function. To put the corner at 100 Hz or 628 radians per second, I will multiply all these by 628. So here's the poles. And now check. I might have to tweak the corner frequency a little bit to meet the requirements. So I'll first build the filter. Here's my poles. I want to check the gain. What's the gain at 400 and 100 Hz? That's F. Omega is 2 pi F. S is J omega. This is the gain. At 100 Hz, the gain is 0.98. At 400 Hz, the gain is 0.02. That meets my requirements, so I kind of got lucky. I'm done. So the net result is, here's one possible filter you could choose. There's lots of other ones. If you choose that filter, then at 100 Hz, the gain is 0.98, meeting the requirements. At 400 Hz, the gain is 0.02, meeting the second requirement. So, kind of thing to note, if you have a 4:1 ratio in frequencies, that's actually fairly easy to design. Problem 2 is a tougher design. I want the gain to drop down to 0.1 when I'm only 1.3 times higher, when I go from 100 to 130 Hz. In that case, you calculate the number of poles you need. I need at least 8.77 poles. So let's round up to 9. Ninth order Chebyshev filter has this transfer function. Scale the poles by 628, 100 Hz, and here's what the poles are. Now let's check. I'll throw this into MATLAB. Here's my 9 poles. Find the gain at 100 and 130 radians per second. That's frequency. S is J omega. Calculate the gain. The gain is 0.97 at 100 Hz, 0.01 at 130 Hz. So this meets the requirement. Again, there's other designs that work. This is one of them. That's problem number 2. Problem number 3 is come up with a circuit to implement this transfer function. When I have real poles, I can just use an RC filter. So to avoid loading, I'll increase R by 10 times, go from 1K to 10K to 100K. The first one, I want to have one of our RC is 2, one of our RC is 5, one of our RC is 10. That solves for C. Then to match the DC gain. This has a DC gain of 1, so at that point I'm done. If I want to give it a little bit more power, just throw in an op amp with a gain of 1, which is a voltage follower. And here's the circuit. That's one possible solution. Problem number 4 is a filter design. If I want to implement this filter, I split it up into 2 halves. The first circuit has a pole at 30 at plus minus 22 degrees. The second one has a pole at amplitude is 30, angle 67.5 degrees. One of our RC sets the amplitude, so one of our RC is 30, C is 333 nanofarads. The gain sets the angle. 3 minus K is 2 times the cosine of the angle. Want a gain of 1.15, making this 15K. Second stage, same thing. One of our RC is 30, R is under K, C becomes 333 nanofarads. The angle set by the gain, I want an angle of 67.5 degrees, means K should be 2.23, making this 123K. The total DC gain then is the product of the two. 1.15 times 2.23 is 2.57. That's for Butterworth filter. Problem 5 is repeat for a Chebyshev filter. It's really about the same. The first pole has an amplitude of 20, so one of RC is 20, makes that 500 nanofarads. The angle is 38.5 degrees, so 3 minus K is 2 times the cosine of the angle, K is 1.43, making this 43K. Second stage, amplitude is 33, gives you 300 nanofarads. Angle is 77.8 degrees, gives you gain of 2.57. And this is 157K. The resulting DC gain is 1.43 times 2.57, 3.69. The last one is an analog computer. Given this circuit, implement it, I would have 3 integrators. That's these guys right here. The gain 1 of RC is 48. So here this is 1 of RC is 48. This has a gain of 44, gain of 12, gain of 1. These are inverters. That's right here. And I could build a second inverter up here, or since I've already inverted that signal, just pull it up over here. That's the red wire with a gain of 3. So that's problem number 6. That's quiz number 3 for ECE 321 Analog Electronics.